We've learnt about adding binary numbers together and converting them from denary and converting denary numbers to binary numbers. To do this section, really you must be very competent at that. You're probably going to make mistakes. We all make mistakes. But I do expect you to have a grounding and a confident grounding in that before you even attempt this. And to be honest, I'd be very surprised if anybody attempts this. It would be nice to know. If you do, please drop me a line and tell me how you get on. What we're going to do is learn how to subtract two binary numbers. It's not easy, and there's a lot of theory behind it, and I'm going to change quite a lot of what you already know. And really, because we're doing data representation with numbers, this really comes into its own. And one of the things, if you want to research this and look online, is you'll find it under something called 2's complement. But I'll go through that, and we'll use 2's complement in here. But if you really want to become an expert in it, then you probably need to research. This would probably be presented at A level, probably at degree level. So it's not an easy task, but it's nothing that you should not be able to do. So let's get on with it. I'm going to reproduce this table. In fact, I'm going to change this one a little bit later on. You should be familiar with this now. This is the binary to denary conversion, and I've only included this at the moment so that I can refresh your memory on the fact that we start at 0 with 4 zeros and we finish off at 255 with did I say 4 zeros? I meant 8 zeros with 8 ones. And we've got every single pattern or combination of patterns of ones and zeros through here. So this is quite a useful lookup table when you want to convert between denary and binary. As I said, I'm going to change it shortly and give you a different representation. Remember, this is data representation and we're going to use it to its fullest. So I'm going to change also the way we look at things. I'm going to start off small and work my way up. I'm going to pretend that my computer is just a 3-bit computer. That's as much as it can handle. So this one here can't handle 4 bits. It would be an error. And I'm going to kind of show you also a 4-bit computer, nibble size, and see the difference between the two and the fact that it's sort of gradually getting too large for us to play with. So you should be familiar with the terms MSB, for most significant bit, being the largest binary value in our bit pattern, and the least significant bit is always the first one, the first digit in our binary pattern. And if I've got 3 bits, the most significant bit is this one, and the least significant bit is this one. So this is 0, 1, 2. And in a 4-bit computer, the most significant bit is the 3rd bit, or actually the 4th bit, bit 3. That's 0, 1, 2, 3. We're going to look at 8-bit and we're going to look at 16-bit as well. So I need this comparison to go forward. So at the moment, you have happily done this, all the different patterns that are possible with 3 bits, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And we have the numbers, the denary numbers next to them, 0, 1, 2, 3, 4, all the way up to 7. Because there's 3 bits, that's 2 to the power of 3, which is 8. There should be 8 values, 1, 2, 3, 4, 5, 6, 7, 8. And they should be numbered from 0 to 2 to the power 3 minus 1. That's 8 minus 1, which is 7. We're going to do the same with the 4 bits. So I've got a nibble, and this pattern is the one that I've told you is most important for you to remember how to write it down. Up to the point where it's 7, it's sort of identical to the 3-bit one, but I've got a 4th bit, a 0 on the front. And then from 8 down to 15, I repeat the pattern here, 0, 0, 0, 0, 0, 1, 0, but with a 1 in the front. And because it's 2 to the power 4, which is 16, I've got 16 values. So from 0 to 2 to the power 4 minus 1, that's 15. I can represent the digits 0 to 15. Okay, so that's old hat. We've done that before. I'm going to change something now. There are 8 distinct numbers in a 3-bit pattern, and there are 16 distinct numbers. Distinct means definitely different to the next one. Numbers in the 4-bit pattern. And we call these unsigned numbers. You probably know them as whole numbers or just the positive numbers, but in computing, they use the term unsigned. So if we've got negative numbers, we call those signed numbers. So let's take a look, and this is our first big difference. If I've got to represent with 3 bits both positive and negative numbers, then I'm going to use the most significant bit, and I've coloured it here in red, to tell me whether it is a signed, in other words it's positive and negative, or if it's an unsigned number, meaning it's just a whole positive number. Big distinction. If I'm using 3 bits, then this bit here in front that I've coloured red is telling me whether it's positive or negative. So this one here is positive 0, this one here is positive 1, positive 2, positive 3, and I've left the rest blank because now I've got a 1 on my pattern. It's only the same, I've only coloured them red. I've got a 1 on my pattern, which indicating that these are negative numbers. So if I can only have, let's say, 8 distinct numbers, and I need them to be positive and negative, then I can only have 4 positive and 4 negative numbers with this bit pattern. Similarly with a 4-bit bit pattern, I'm using my most significant bit to say whether it's a positive or negative number. The 0 means it's positive, and I've put that 0 to 7. And I've left this one blank at the moment because I'm going to fill it in a minute, but these are negative numbers, and again repeating the pattern. But because there are 16 distinct numbers, if I want to represent positive and negative numbers, half of them are going to be positive, half of them are going to be negative. That's 8 positive, 8 negative. So at the moment, I want you just to fix that in mind, to understand that half of the numbers are negative, half the numbers are positive if we have signed binary. So let's take a look. If I have signed binary, I have a little bit of difference in my counting. Let's take a look at the 3-bit pattern. I went 0, 1, 2, 3, and then they were all my positive numbers. Now I've got my negative numbers, but we do the negative numbers from the bottom upwards. So -1 is always the bottom number. It's always full of 1s. So that's negative 1, 1. And then -2, -3, -4. And that is all the numbers I can represent with 3 bits. I can start off with my largest being 3, 2, 1, 0, -1, -2, -3, -4. They are all the whole numbers I can represent, positive and negative, with 3 bits. It will help us do some work by looking at these 3 bits because we lose the sort of precision of 8 bits or 16 bits. It could get confusing, or more confusing, with larger values. And I do the same with my 4 bits. Now remember, I didn't fill these in, I've just put the values in now. Remember, I start at the bottom with my -1, -2, -3, -4, going up, -5, -6, -7, -8. And so this bit pattern here, 1000, is the binary pattern for -8. This pattern here, 1001, is the binary pattern for -7. Let's go over to the 3 bits. -4 is 100. that represents -4 in sign. If we take a look over here, -4 is 1, 1, 0, 0. So it's a little bit strange and a little bit different to what you've been doing so far. So how to make these? We start off with the bit pattern. We need to know how many numbers there are. So if I've got 3 bits, I know that's 2 to the power 3. I've got 8 different values. Because they're signed numbers, half of them are going to be negatives, half of them are going to be positives. I start off with 0 and I write down half of them. Half of 8 is 4, so I do 0, 1, 2, 3 and just use the normal binary pattern. There's nothing different in this. This is just the binary pattern you wrote down. I've only coloured in the very first digit. But I don't continue 4, 5, 6, 7. I start at the bottom counting -1, -2, -3, -4 going upwards. And that is the bit pattern that the computer recognises as a minus number. I do the same here. Got 4 bits, so 2 to the power 4 is 16. Half of 16 is 8, so I've got my 8 positive ones. And this pattern here is just the same. I haven't changed anything in the pattern at all. I've just used the leading bit, the most significant bit, to tell me whether it's positive or negative. So I've written down the first 8, 0, 1, 2, 3, 4, 5, 6, 7. There's 8 items there, and then I do the negative starting at the bottom and count back up. So that is a quick look. I'll finish this video here. We'll move on to the next video to see how we can play around with this information.